Okay, Zoom folks, can you hear me okay?
Yeah.
Yep. Okay, quick question for you. When I pin video, right, if I just clicked pin video, does that pin the video for all of you or just for me? So right now my video is pinned, which means that at least on my screen, I'm the one that sees, like I see myself. But if I click unpin video, I just, see people's names and things like that. It's just me. Okay, perfect. Good to know. So I don't really have any control over any of this. You can pin me if you want. You don't have to. But you at least have that option. That's good to know from my end because still not super Zoom user. All right, so let's share the screen. Okay. Okay, so before we get into the material, let's assign project groups for those of you that have a group member here. So I know that some of you did email me the groups that you wanted, but I did not go in and add those to the list because I wanted to kind of do this in order, based on the random numbers, just in case there was any kind of competition for a particular data set. But based on the results that I was getting, by email, I don't think that's going to be a problem, but let's go ahead and go through the groups in this order, which is an order by a random number. So group 2, are you here? Do you have a representative that will claim one of the data sets for your final project?
Yes, so we were thinking we wanted I guess life expectancy.
Okay. Group 3 is the next one. Do you guys have a preference on your data set?
Yeah, can we take the Vino data set?
Is it Vino Verde? Like, how you spell it? Okay.
Yeah, exactly.
And the next group is group 5.
We wanted the Vino as well, if that's okay.
Yep. Group 6.
Hi, can we do housing prices?
Yep. Group 4.
Could we also do life expectancy?
Yep. Group 7.
Can we do housing prices?
9. Anybody from group 9? All right, group 1.
Hey, I think we're going to go with temp health on this one.
Okay. And group 8.
We would also like to do temp health.
Okay, all right, that's great. So I was thinking that as many as 3 could do a single data set, but if that's kind of how you guys wanted to do things, then that's fine. That's great. That's a perfectly even distribution. And then group 9 can let me know whenever they get a chance. So I do want to do a little bit more work in R before we do the module lecture, because I know that you have a homework assignment coming up, and there were some questions about that, and so I've given you some resources that I think will help. I do have a couple of emails outstanding that I need to respond to, and if you don't hear back from me by, like, I don't know, 3 p.m. today, with my kind of looking at your script and helping you troubleshoot the issue, just follow up with me. But I should get the email backlog cleared by this afternoon. And there are a couple of things that you might find useful on ELC. So the first thing that I posted is a a solutions document for homework 5. So if you would like to see the solution for homework 5, I've posted it as our markdown file and then also as a Word document. As long as you've submitted something to the folder for homework 5, you can download that. If you haven't submitted anything yet, then you won't be able to download that solution document. And I think that that will be useful in case you're having trouble separating out the months and the days with LubriDate, because that's something that we did on homework 5. And so if you are struggling with it for homework 6, then just review the way that it's set up in homework 5 so that you see kind of how I did it. And there's other ways to do it for sure, but how one way that you can make sure that you get the months and the days pulled out of the data set. The other thing is, and I don't know if this is up. No, I will post one more video that has it's an exercise that's very similar to the homework assignment, and I'll work my way through it so that you can see it. I think I've posted it to the other class section. I haven't posted it to yours yet, but I'll post it to yours as well, so that you'll have that as well if you'd like to look at it. So those two resources you'll have, and then other than that, feel free to shoot me an email. I'm pretty available, and if I have not yet responded to your email from over the weekend, I'll get to it by this afternoon, and if not, just ping me to remind me. Any questions about that? Okay, was that a question?
6, yes. 6 and homework 7 are like due delayed according to ELC. Is that still right? Like, is it both of them or is it just homework 6?
I did not catch what you said.
Sorry, can you hear me now?
Asking about the due dates for homework 6 and 7.
Oh, so it's just homework 6 that's due, right? Homework 7, I don't think I've adjusted the due dates on ELC for everything past that. So homework 7 is not due yet. So I'll adjust those due dates, over the next few days. I'll adjust them down. But that revised syllabus has kind of our most up-to-date due dates on it.
Okay, thank you.
So there is a reading quiz coming up that's over the last 2 chapters of the book, and then also the project proposal coming up. So those are the 2 kind of deadlines that are coming up. And if you have questions about that, feel free to let me know. The quiz should be live on ELC. You should be able to see it. So let me know if you have any questions about that. All right, so let's pick up kind of where we were in R, right? So when we went through this last class, we went through it kind of quickly to make sure that we were all kind of on the same page about regressions. And so, we did rush through it, but it sounded like we were all on the same page, which is very good, right? So we started by looking at this merged data set of our means and CO2s. We did a correlation test. We found that there was a correlation of 0.48. We said that the correlation is R. It's not R squared. It's not the coefficient of determination. So you can't interpret the correlation as percent of variance explained, right? That's an R squared, not an R thing, right? And then we started to look at some of the ways that you could, in R, look at some of the regression kinds of statistics. So the first thing that we did was we built a scatter plot, right, of our means and CO2s. And in this case, we added a linear trend line, so that's G on smooth. And so here's our just basic CO2s, means, observations, linear trend line. So that's going to be our regression line. And then our default confidence interval is at 95% confidence interval, right? We've had some practice creating linear regression models in R. So we can assign an object, right? In this case, model 1 or mod 1. And then we'll use LM for linear model. And then we'll specify $m mean, or the mean of the temperature, as our dependent variable, and then CO2 as our independent variable, right? And if we run that line, what do we get? We get a list in our data environment. So model 1, it's a list, or mod 1. And so you have all of the sort of regression information in that list. Now, if you want to see sort of your summary of your regression, summary mod 1, and there you get your intercept, you get your coefficient estimates, you get your significance levels, etc. Right? And so if you wanted to predict the mean temperature at 400 ppm of CO2, you take your intercept, 48.24335, and you add 400 times your coefficient estimate. And if we do this, then we get 55.98 degrees, right? So that's 400 ppm of CO2. And our predicted value is about 55.98 or 56, right? And that sort of lines up with what we have on this graph, on this plot. Any questions so far? So that's a review of what we did last class, which was also a review then. So we're just, it's a new week. We're just making sure that we do a quick 2-minute catch up over everything that we've done so far. So any questions on this? So there's a few cool things that we can do when it comes to plotting residuals, right? So, the easy way to do it is just plot your residuals in ggplot. In this case, what I've done is I've added another geom, right? We say that the way that ggplot works is that we start by putting together the plot, right? The gray square with the aesthetic elements, in this case, the residuals and CO2. And in the script that's on ELC, by the way, I think it just says mod residuals. So make sure that it's mod 1, which, right here, because that's the name of the model. But the other thing that I've added is a geom H line, or horizontal line, that just goes horizontally across the y-intercept, so that we can see that we want a normal distribution of our residuals above and below that 0 point, right? Because we want to ensure that they're normally distributed without any kind of systematic pattern or bias or anything like that, right? So that's the easy way to plot the residuals. The other thing that we can do is we can use this package called Broom, which you can install if you like, and then augment your model and create a plot that actually looks at each of that plots the residuals in red lines, right? So you can actually see the distance with from your observed values to your predicted values that live on the line, right? So something that you can do. And so what we did here was we just used Broom to augment model 1. We called it mod 1A. And then we just used ggplot to say, okay, we want to take our data from CO2 and mean, but we want to create this segment, right? And the segment is going to be the one thing that we're going to add, right? So then we can do a little bit more with plotting residuals. Now we're actually going to do a residual plot a third way, but these are the two ways using ggplot that are kind of interesting, and they look nice, and you can do all kinds of things. But we'll look at an even simpler way to go ahead and plot all of the residuals as a part of kind of a package of robustness tests on a regression. So with that, so the last thing that we did, and I think you had the answers for this, and I showed you the solution video as well. We could do this using Superstore. And so the way that we would do that is by reading in Superstore. And I did post the Excel version of Superstore in case you were using the CSV version and your code didn't match up with mine exactly. I had the Excel version, or an Excel version from last semester. That was the one that I'd been using at home. So you have that as well now. It's in the most recent R kind of folder. So the correlation coefficient, just core.test. And then you can test between Superstore sales and Superstore profit, create a scatter plot the same way, and then run your regression model residual plot exactly the same way as before. So what if we have multiple predictor variables, right? Multiple regression model. This is something that you all are familiar with. How do you actually make R understand how this works? Well, all you need to do is use so your dependent variable here is profit, right? We're trying to predict profit, which makes sense as sort of a business task, right? We want to predict how we can achieve the most profit. We're still using sales as one of the predictors, but we're also using discount as one of the predictors, right? We're saying, in theory, right, this is, our explanation, our theoretical explanation. If we discount things to a very high level, then our profits are probably not going to be quite as high, right? So we hypothesize that there's a relationship between discount and profit, and we would hypothesize that that's a negative relationship, right? And it turns out that there is a relationship, which we can tell by the fact that that coefficient estimate is significant, right? So here's the discount coefficient estimate, and there's the estimate itself, and there's the significance, right? We got 3 asterisks. That means that it's highly significant, which means that there is a relationship between both sales and discount on profit, right? We do see that there's a negative sign here on the coefficient estimate. What does that mean? That means, like we would predict or like we would expect, that the relationship between discount and profit is a negative relationship, right? So the more you discount, the less profit you make on each transaction. Again, which makes sense, but that negative sign supports that claim, right? And then the strength of the relationship, well, we can say, okay, what's the R squared? 0.27. So with sales and discount, we can explain about a quarter of the variance in profit. So again, the thing that we are doing here above and beyond what we've done before is just adding our second predictor variable just by saying plus and then whatever that variable is, right? So everything else is still the same. You assign the name of your model, and then LM is linear model, and then formula equals your dependent variable, and then your sort of squiggly tilde thing, and then your independent variables, which are connected with a plus sign, and then you specify the data, right? And then summary of the model, and that's it, right? So there's some things that, well, let's stop here. Do we have any questions on this so far? Like this is, I didn't explain, the multiple regression part of it, right? But my assumption is that you've done multiple regressions. You know that each coefficient is sort of assuming that everything else stays equal, et cetera, right? Yeah. Any questions on this? Wait just a second. Okay, so we have some ways to robustness tests for our plots, right? Like we said, residual plots help us test, in this case, the variance around the regression line should be the same for all values of the predictor variable. A couple of other predictor plots, QQ plot. Did you guys look at QQ plots in your stats class? This is a thing that y'all are familiar with? I'm thinking maybe not. That's okay. So a QQ plot helps us test the normality assumption of the linear regression model. So what we want to see ideally is a solid line, we want the observations to occur along the line, which they are not doing here, which we know that our superstore data is a little bit funky along this kind of axis, right? So the data has some very high standardized residuals. It might not meet the linearity assumption of a linear regression. We really want to see that that QQ, the dots lie along this line itself. And then Cook's distance. Cook's distance you guys did look at, right? In your stats class, you're familiar with Cook's distance, I believe. So Cook's distance measures the influence of each individual observation on the coefficients. And so the way that it's calculated is by looking at the change in the model estimates when you remove a particular observation, right? And so the sort of rule of thumb for Cook's distance is that a Cook's distance over the number of predictors divided by the sample size is noteworthy. And so our Cook's distance numbers are very high in this model because of 3 particular observations, right? So there's 3 that are highly skewing of the regression coefficients, and we can go in and look at which observations those are if we want. So now those are the 3. Those are 3 of the robustness tests that we'll use, right? As you likely know from your stats class, those aren't the only 3 robustness tests for linear regression. But those are three that we'll look at and we'll model. So fortunately, there's a very easy way to model basic diagnostic plots. And that is simply plot and then mod 3, right? So what happens if you put in plot mod 3? Well, it's going to give you a bunch of different diagnostic plots. And in this case, we can specify that we just want 1 through 6. And if we do that, right, so plot mod 3, and then you say which equals 1 through 6, you can go down into the console and hit enter 5 times, I guess, and see all of these plots. Now, that's not the most effective way to do things, right? And it gives you plots that you may not want, right? Cook's distance versus leverage. That looks like it's complicated. I don't 100% know what's going on there. So, we maybe don't want all of these at once. So what we can say is that we would want to specify that we want a 1 row, 3 column kind of plot space, and that within that plot space, we just want plots 1, 2, and 4, right? So if we look at what the first one was, the first one is our residuals, which we know how to interpret, very simple, right? The second one is our QQ plot. We know that we want it to be along this dotted line, and it's not. And then we don't need the square root of standardized residuals over the fitted values, but we'll maybe use the Cook's distance one, right? So we say we're going to specify that we want an arrangement of one row, 3 columns, right? So that's what this PAR line does. Then we're going to say we want plots from model 3, which plots just 1, 2, and 4. So now if we run that line, that's I guess line 91 on mine, then you have something that looks very nice and easy to drop into a report to help visualize your regression diagnostics, right? You can get a sense of, okay, in this case, you're looking at pretty even spread above and below the line. There's not too much kind of weight drawing that down, but you do see some issues in the QQ plot. You do see some issues in the Cook's distance, and so you can take that and interpret it the way that you would like to, right? Maybe you can remove some outliers and see what happens. Maybe you can say that the issue is that the linearity assumption is not met, which means that you need to think about using some other kind of model, right? Maybe a logistic model, maybe something else altogether, right? You need to add a quadratic term, something like that. But for the purposes of this class, maybe you can look at outliers. But my sense is that if you are not, so you should report your, at least these 3 diagnostic plots, and then you should make an assessment about whether or not they are, your regression meets the standards that you lay out, right? What that means, you should interpret those plots. And then if you, don't know what to do next, that's okay. I would say in your report for your final project, say, this is something that we need to uncover more, right? This is something that we need to consult a stats expert on. This is something that we need to look into in greater detail, right? So you can say that our conclusions may change with additional analysis or something kind of wishy-washy like that. But what I do want to see basic diagnostics, and then I want to see you interpret those to say, okay, is it good? Is it bad? And then if it's bad, you can look at some things, right? Maybe in this case, you could remove some outliers and recalculate Cook's distance. That would be about as far as I'd expect. I wouldn't expect you to go, adding a quadratic term or, doing something like that. That would be beyond the scope of this class. So are there any questions about this so far? We did again, kind of at an aggressive pace, but we added a predictor variable, right? So we're squarely in the land of multiple regressions now. And then we looked at some ways to create diagnostic plots fairly simply to get a sense of whether or not our predictive models are any good. Let's do a 1 through 5 in chat. How are we feeling about regressions in R based on the things that we've talked about? So we did go through this quickly, but my sense is that y'all are in good shape. Okay. All right, those numbers are much lower than I thought they were, so I appreciate you all letting me know. That's good to know. So for those of you that have lower numbers, is it the R part of it, or is it the regression part of it that's more confusing? I guess you can chime in either in chat or on voice. The regression part. Okay. The R part. All right. So looks like both parts, and the numbers are lower than I was hoping for. So let me go over this one more time. And so I guess we got the fast version. We'll do it a little bit slower now. So we know what we were doing with the simple linear regression, right? What we were doing with the simple linear regression was we were building a model which could help us predict, for example, what the mean temperature would be at 400 ppm of CO2, right? So, for example, we have this linear best fit line, right? And what we have on this best fit line are a bunch of observed values, right? Those are our black dots. And so the observed values are actual temperatures with actual CO2 amounts, right? So it's like, let's say every year, and I guess this is every month, and then we averaged every month, right? So every month, I go and take the temperature in Central Park, and I go and find out how much CO2 in ppm is in the atmosphere, right? And then I average that year over year, okay? So every year I have a mean temperature for Central Park and an atmospheric CO2. And those are my actual measured amounts, right? And those are the black dots. Now, what a regression does is it creates this line, right? It creates a best fit line. And the way that it creates the best fit line is by minimizing essentially the distance between the dots below the line and the dots above the line, more or less, right? And so the idea is that these red lines here, and those are called our residuals, should kind of roughly be equal above and below the line, right? That's a regression. What does the regression line give us? It gives us a sort of a set of predicted values. So what are we able to predict? Well, we can predict that if the atmospheric CO2 in ppm is 400, so 400 parts per million of CO2, then the temperature, the average temperature over the year in Central Park is going to be 56 degrees, right? So that's what a linear regression does. That is a simple linear regression with our dependent variable being mean temperature and our independent variable being atmospheric CO2. So we are predicting mean temperature and we can explain some portion of mean temperature, right? That's what our R squared tells us. So what are we able to predict? Because our R squared is 0.23, we can predict about a quarter of the variance in mean temperature. What are the things that we said last class? Well, there's other things that affect mean temperature, right? For example, the cloud cover. On cloudy days, mean temperature is going to be lower. On sunny days, mean temperature is going to be higher, right? And so there are other things that will take up some of that variance that could be explained, right? Potential variance explained. But in this case, we are explaining about a quarter of the variance in mean temperature. Right, so that is a simple linear regression. That is one dependent variable, one independent variable. And what do we know? We know that there is a relationship, and we know that because there's a significant model and a significant coefficient estimate, right? So there is a relationship. It's a positive relationship. We know that because the estimate is positive, right? And we know that there is the existence of a relationship, the direction of the relationship, and the strength of the relationship we can talk about with respect to the R squared, right? The amount of variance explained. So those are the three things that I want you to think about, right? Is there a relationship? Yes or no, which you'll base on the p-value, right? Which we say are your results kind of, can they be distinguished from chance or not? And then do you have, what is the sign on your coefficient estimate, and then what's your R squared? Okay, so that is a simple linear regression, right? What did we do to build on that? Well, okay, so let's talk about the R, right? And we won't do this broom thing because this is just kind of above and beyond. But what we do want to do is we want to be able to plot the residuals using ggplot2, right? So the way that we're going to do this is we're going to first, load ggplot2 into memory using library ggplot2. And the function is going to be ggplot. And the data set that we're using is M, right? M is the data that we brought into this. It has our means and our CO2s, right? And so so the first thing that we need to do is specify the data set. The second thing we need to do is specify the aesthetic elements, right? The aesthetic elements give us basically the box, and then the axis, what's going to be in the graph, right? So what are we going to put? We're going to put the residuals of model 1, right? All of these amounts, right? So like if this amount is some number, we're going to put that number in, right? And then on the x-axis, we're going to put the CO2 numbers, right? And so if we do that, we see each of those residuals now. So instead of plotting it like this, where this line is sort of at an angle, right? You basically are taking that line and putting it at 0, and then saying, okay, what is the relative distance of those residuals above and below it? That's essentially what you've done, right? So you said, okay, the y is going to be the residuals. The residuals live inside of your model 1 list, right? So you got model 1, it's in your environment. One of the things in your model, in your list, is a set of the residuals, and these are the numbers of the actual amounts, right? So you can see that you've got the scale. It goes from basically 0 to 2, 0 to -2, and these are all the actual residuals. And if you look at this version of it, it's essentially the same, right? So here's let's say 400 ppm, 56, right? This particular residual goes from just over 56 to about 56.5, right? So it's a residual of 0.5 or so. And so that's one of the residuals that we are plotting, right? And this is a way that we can assess how good our regression model is. So again, how did we do that? ggplot. M is where the data is coming from, right? And so R is telling us we don't need to say $M CO2. But for Y, we do want to say mod 1 $residuals, because the residuals live in this list. And then X is CO2. And then if we don't add in the next layer, right, all we have is our gray box, right? So we need to say, okay, we need a geometric element. So we're going to put a geometric element of points that are blue to represent the data. And then we're also going to put a geometric element that's a horizontal line at the y-intercept of 0. And then we'll add an X label, right? So that's the elements of this graph. And that's our residual graph, right? So that is the sort of the stats, and then the R of a simple linear regression. So then if we want to, right, we can take our simple linear regression and say, okay, now we have multiple variables of interest in our sample of observations, right? So now instead of just looking at, let's say, sales and profit, right? We want to see, does sales predict profit? We can say, okay, do sales and discount amounts predict profit? We can build a predictive model that's a little bit more complex, a little bit more sophisticated than just a simple one predictor, one dependent variable model, right? So what does that do? Now we're building a model that says, okay, profit is still our dependent variable, right? We're still trying to predict profit, but instead of just sales, we have sales and discount in our model, right? So here, profit is our dependent variable. You've got your squiggly and then sales plus discount, right? So everything is the same as it would be for a simple linear regression. The only thing that you're adding is plus and then the other independent variable on that call line, right? Now you have one intercept still, obviously, right? But you have two different coefficient estimates. And the way that you would interpret those is if all else stays the same, then you can use one of those intercepts or one of those coefficient estimates to predict where, the profit would be if sales were $500,000 or whatever the situation may be, right? And so in this case, the way that we interpret this, right? Is there a relationship? Yes, we have we see lots of asterisks, right? We see that our p-value is less than 0.05, right? So we say, yes, there is a relationship. The existence of the relationship has been met. You look at the direction of the relationship. So the sales has a positive relationship with profit because that sign is positive. Discount has a negative relationship with profit because that sign is negative, right? And then what is the strength of the relationship? Well, by adding this predictor variable in, we can now predict, we can now explain a little bit more variance in that outcome than we otherwise could, right? So that's the R squared amount, right? Now 0.27. So we can explain over 1/4 of the variance in profit by adding by using a model that takes in sales and discount. Okay, so there's different diagnostic plots that you can use to assess whether or not your model is any good. So for example, you can look at your residuals, right, versus your fitted values. And so in this case, we're not going to get into the math about it, but there is a link in the slide notes if you want to get into a bit more of the math. But here what you want to see is that red line about as horizontal as possible, right? And so what does that help us test? That helps us test the variance around the regression line should be around the same for all values of the predictor variable. So what this is giving us is essentially the same as what we've been doing like this, right? And so what we're saying, what this is telling us is that that's on average okay, right? Now, the issue is that we do see some systematic variance in the way that the residuals are distributed. And that's what gets revealed in our QQ plot. Our QQ plot helps us test the normality assumption of the linear regression model. So any fixed value of a predictor variable, your independent variable should be normally distributed, right? So in this case, we want to see your observations, each of which is a dot, lie along this dotted line, and we don't, right? Which means that what we see is a potential breakdown of this linearity assumption. And again, if you want to get into more detail, there's a link in the slide notes that goes into more detail about that, right? Now the third one is Cook's distance, and Cook's distance measures the influence of each individual observation on the coefficient estimates. And so what this means is that, let's say we are looking at our set of coefficient estimates. And so what Cook's distance says is that each individual observation has some effect on the coefficient estimates, right? These things right here. And so the way that Cook's distance is calculated is they basically remove each observation from the model, rerun the entire thing, and then see how much it moves, right? And if it moves a lot, that means that observation is highly sort of impactful on the coefficient estimates. If it doesn't move that much, that's good, right? That means that most of these observations are relatively consistent with what the model is looking at. And so the model doesn't move. It's not highly kind of explosive with respect to one observation that is included or not included. And so the way that Cook's distance works is you get a distance measure for each observation. And so here on the x-axis here, you have observation number, right? And so you have 10,000 observations, right, or 9,000 observations in Superstore. And so what this is telling us is that observation, what is this, 2668? Let's see this, so like 2698, 6827, 8154. Those are 3 different observations, right? So that is an instance of profit and sales and discount. Each of those observations has a significant impact on the final result, right? And what we should look for in Cook's distance, right? These are diagnostic plots or robustness checks. So each of them has a rule of thumb, right? So this has a rule of thumb where you want it to be on that dotted line. This rule of thumb is you want that red line to be about equal, right, or about parallel, or on the zero, right, etc. So the rule of thumb for Cook's distance is that you take the number of predictors in your model and you divide it by the sample size, right? And if your Cook's distance is greater than that, then you've got some problems, right? Then the Cook's distance is too big. And so here's the Cook's distance on the y-axis. It goes from 0 to 50. The Cook's distance of this observation is up there at around 50, right? It's way higher than our number of predictors, which is 2, and then our sample size, which is about 10,000, right? So it is these 3 are highly noteworthy Cook's distances. And then there are some others that are probably noteworthy as well, but these are the 3 that you would definitely want to look at as potential outliers, etc. Right? So that is Cook's distance. And then the last thing is multicollinearity. Multicollinearity is it exists when you have multiple predictor variables that are highly correlated with one another, right? So in this case, if you have the model that we were using was sales and discount. And so if you have a correlation within your predictors, so in this case, within sales and discount, what that can do is create instability in your model. If there's a lot of covariance that exists between or among sales and discount, right? We're trying to predict profit, and the predictors we're using are sales and discount, right? And so we can use what are called variance inflation factors to test whether or not there is a problem with the amount of multicollinearity in the model. And so the way that we do that is by opening up the package car and just VIF and then the name of the model, right? So in this case, model 3 is going to be profit and then sales and discount as independent variables, right? We've looked at this already. We've said that, okay, it's a significant model. Sales is significant, discount is significant and negative, right? And then we can sort of, do our plots, which we saw. We saw that we have our Cook's distance numbers that are a little bit too big. We have our QQ plot that's definitely not along the dotted line, but the residuals, taking out of account the normality, the numbers themselves are okay, right? You're seeing kind of balance above and below the line. So the residuals, not bad, but not normally distributed, which is part of the assumption of a linear regression. And then your Cook's distance is showing you that you have some outliers that are really affecting the model. So then our variance inflation factor says, okay, is there an issue with sales and discount having so much internal covariance that creates instability in your model, right? So what are you looking for? You're looking for a VIF that's larger than 10, right? Some people say larger than 5. If there's a VIF that's larger than 5, then you might have problems, right? But for this class, we'll say if you have a VIF value that's larger than 10, then you have some problems. You should maybe consider dropping one of those variables, right? So in this case, library car. Car is a companion to a regression book. And then just VIF of model 3. You can see that the variance inflation factors are 1, right? 1.00. So we don't have any multicollinearity problems in this data set. Any questions about that? Okay, so let's do a 1 through 5 in chat again and see what the numbers look like. Just to see kind of where we're at, both in terms of R and in terms of the the regression stuff. See if the vibe has kind of gotten a little bit better since the last time that we checked. All right, well, I'm not seeing 2s, which is good. I hope that what that means is that the people that gave me 2s earlier either are getting it better or they've, they're still working on it. But if you have issues, let me know. And I will post up another optional video where I'll go through this in sort of step-by-step detail for those of you that are still kind of struggling with it. Okay, And then let's work through an exercise, because I think that that's a good way for us to make sure that we've got a good sense of what's going on. So there's this Excel file on ELC called Denver. And Denver has some data about different neighborhoods in Denver, Colorado. And specifically, we'd like to use this data to predict which neighborhoods will have the highest crime rate, right? So our crime rate, that's X6. So the label, the different columns are just labeled X1, X2, X3, X4, X5, X6. But our dependent variable is going to be X6, crime rate per 1,000 in the population. And then we have some predictors, right? Total population, change in the population over the past several years, number of children, number of free lunch users, or percentage of free lunch users, percentage change in household income over the past several years, and then change in crime rate over the past several years. So we don't need to use X7, but X1 through 5 can be our predictor variables, right? So our dependent variable is going to be X6, and then X1 through X5 will be our predictor variables. So then I'll give you some time to work through this, but we'll go through it together. And you can see in the slide notes, there's a link to a YouTube video where I go over this, step by step in detail, right? So if you're totally lost on this exercise, then click through the YouTube video and you get a chance, this evening, and you can watch me go through it in detail. But I'll give you, a little bit of time to look at number one. What is the single predictor variable from X1 through X5 that significantly explains the most variance in crime rate per 1,000? That's X6. And then what is the R squared? So it's 1023. I'll give you until 1024. I'll give you until 1027 to tell me which single predictor variable explains the most variance in crime rate. All right, it's 10:27. So let's see, how many of you have an answer? Let's see, maybe a wave or something in chat if you have an answer. All right, I'm seeing 0 waves. That means that nobody has an answer. Did either of y'all get it in class? Not yet. Are you still working or are you stuck? Still working. All right, still working, still working. I'll give you 2 more minutes, 10:29. Well, I'll go ahead and start too. Okay. Okay, so for those of you that were following along with what I was doing, what I basically did was I did 5 different models, right? I called them Q1A for question 1A, question 1B, C, D, and E, right? So for 1A, I said, okay, we're going to take x6 as our dependent variable, right? We said x6, oh, we don't need that. We need this. X6 is crime rate per 1,000, right? Is our dependent variable, and X1 is our independent variable, right? Total population in thousands. So X6 is our dependent variable, squiggly X1, data equals Denver. So that's model Q1A, right? And then if we look for the summary of Q1A, what do we look for? We look for 2 things, right? First, we look for significance. We do see 1 asterisk, which is great. That means that P less than 0.05, we've met our sort of standard. And then I just made a little comment here, so a little hash, and then the R squared, right? The R squared here is 0.1298. So what does that mean? That means that if we want to predict crime rate in neighborhoods in Denver, total population explains about 1/8 of the variance in crime rate, right? So that's what we've just learned, right? Now what we're doing is we're looking for the predictor that explains the most variance, right? That's what I asked you to do. Which single predictor variable significantly, and I have significantly in brackets there because it shouldn't need to be said. If it's not significant, there is no relationship, right? But what single predictor variable significantly explains the most variance in crime rate per 1,000? So we said that the first independent variable explains about 0.1298, so about 1/8 of the variance, right? Q1b, that's the second independent variable. We look at that and we see, okay, our p-value is greater than 0.05, right? We don't see a star, instead we see the dot. The dot means we can call it approaching significance, which will annoy any statistician. But if you want to kind of squeak it into your report, you can say it approaches significance, and you might get away with it, but it's not significant, right? So what does that mean? That means we move on. We say that there's no relationship. You can say it approaches significance. More research is required, et cetera. But given the data that we have, not significant, right? Q1C, now we're going to look at the third predictor variable. So X6, our dependent variable, hasn't changed. We're still trying to predict the crime rate, right? But now we're going down the list of dependent or independent variables, right? So the one that we just looked at was percent change in population over the past several years. Now we're going to look for percent of children under 18 in the population, right? So that's X3. That's our independent variable. We run a summary on that, and we say, okay, this is also not significant, right? 0.06, very close to 0.05, right? So it really is approaching significance, but it's not significant, right? So if you were, you had a hypothesis about the role of children in a society, right, and the crime rate, right, you could say, okay, it approaches significance. We are not willing to throw out our hypothesis just yet, but we need to collect more data. We need to refine our hypothesis, and we need to refine our model, right? But you have to have some standard, and that standard is 0.05, right? Okay, so X4, that's a percentage of free lunch in that neighborhood, right? You run that model. X6 is the dependent variable. X4 is the independent variable. Run summary. Okay, now we do have asterisks, right? That means that it's significant. Our p-value is 0.005, which is much less than 0.05. And then your r-squared is 0.1727, right? That's bigger than your 0.1298. And we have one last independent variable to test. That's X5, or the change in household income over the past several years. So we run that test. We see, okay, we do also have significance again. And that now we're explaining 0.1663 of the variance in crime rate, right? So slightly less than our 0.1727 model. So what is the model that explains the most variance in crime rate? For the single predictor, well, the single predictor is students on free school lunch participation. That predicts crime rate, right? Now, again, we're not saying that free lunch causes crime rate, right? We've talked about causality. We know that we can't infer causality from this case, right? But now what we've said is that there is a correlation between these two variables. We can predict the variance in crime rate based on the percent change in the percentage of free school lunch participation. Any questions on what we did there and what we were asking, what we kind of found out? Okay. So the next question that I asked you is to construct a regression model. Oh, is there a question in the chat? All right. We'll work on it. I think that once you do the homework assignment, we'll get there. But I appreciate the honesty. I do. Okay. So now we want to use 3 significance predictor variables that can explain more than half of the variance in crime rate per 1,000 of the population, right? So that's our dependent variable. Dependent variable hasn't changed, right? Now we're going to try different combinations of independent variables to see if we can find 3 significant ones that'll explain over half of the variance in crime rate, right? And just like sort of this first one, it's a little bit of guess and check. And if you watch my video about this, I come up with some kind of hypotheses on the fly. I say, okay, well, this might explain this part of it, and this might explain this part of it, and this might explain some other part of it. But what we do ultimately is we build a model with one dependent variable, right, which is always going to be one dependent variable, and then now 3 independent variables. So I'll give you a couple of minutes to work on it, see if you can find a set, and there may be more than one. I know that I have one if I scroll down, and then we'll come back in and we'll see if we found one. So it's 10:37. I'll give you until 10:39, which will give you maybe one shot at it, maybe 2 shots to build some models. All right, so let's construct a regression model that uses 3 significant predictor variables to explain more than 50% of the variance in crime rate. So again, let's go ahead and we'll come up with a model, right? So we'll call it Q2 for question 2. And our formula is going to be similar, right? It'll be 3 different variables, right? And then our data set. So now we've got to think about how we're going to decide what 3 we're going to pick, right? And there's different ways to go about this. But one of the way that you could conceivably think about it, right, is that these both X1 and X2 kind of think about population, right? Both total population and the change in population. Of those 2, change in population is probably more of a predictor because it's at least a little bit dynamic, right? If population is kind of going down, if a neighborhood's like in decline, people are leaving it, change in population is going to show something. So let's add X2 to a model, right? We know that free school lunch is the strongest single predictor, so let's add that to the model as well. And then the change in household income, we know that was significant and fairly strong effect. And it captures something that's a little bit different than kids, right? Kids don't really have any income, but it's similar to school lunch participation, right? So we'll see if there's some overlap there, but hopefully between X2, X4, and X5, we'll create a model and we'll see what the overall R squared is, right? But we'll walk through the process of interpreting it, right? So what are our independent variables going to be? We said X2, X4, and X5, right? And let's do a summary of Q2. So we've created a model, and literally the way that we did it, we kind of did it without kind of explicitly talking about what we were doing. But what we were doing was we were creating hypotheses, right? We were saying, okay, we believe that these things are related to the outcome, right? And these are the reasons why, and these are the reasons why we're picking certain things over others, etc. Right? Let's zoom in and zoom in again. So here's my Q2. Let's create the model. Summary of Q2. Oh, what do we have here? Oh, you know what I need? I don't need those commas. I need plus signs, right? And then now we run that. Now we have a model, right? Okay, so let's see what we did with our model, right? So x6 is our dependent variable. And then our independent variables are x2 and x4 and x5, right? So we look at this model, and we do see that the overall p-value for the model is significant. So the model by itself does show a relationship between our independent variables and our dependent variable, right? But our x2 model, our x2 variable, right? That particular coefficient is not significant, right? So in this model, x2 is not significant, but x4 and x5 are, right? And you can see that these, the number, like the different levels of significance can vary based on how many different things are in the model, right? Because they all kind of add incremental value. So in this case, how much variance are we explaining? We're explaining now about a third of the variance, right, in this model, but we have a dead coefficient, right? There's no relationship here. This is not significant. It's not even approaching significance. It's nowhere near significant, right? So we're explaining about 34% of the variance in crime rate with just x4 and x5. And so what we can do is maybe change x2 to a different variable, right? So we said x2, x4, x5. Let's say maybe children, right? Maybe if there's a lot of kids, that might predict crime rate. You know, they got nothing to do in the summers, whatever the situation may be, right? So let's change that to x3. Now our Q2 model has x6 as our dependent variable, right? Crime rate, and then number of children, free lunch participation, and change in income, right? Now we look at the summary, and we have 3 highly significant coefficients. And how much of the variance do we explain? Almost 60% of the variance in our dependent variable, right? 0.5817. So that does meet our requirements, right? We have a model with 3 significant coefficients, and together they explain over half of the variance in our dependent variable, right? So we're trying to ask, okay, were we able to come up with a model that helps us predict crime in these Denver neighborhoods, right? What you will be doing for your project, right, is coming up with a model to predict high quality vino verdes, right? So you'll say acidity and pH and something else, right? And you'll build a model, and your job will be to build a good model, right? You don't want to stick every single variable in there, but you want to have reasons for the variables that you have, and you don't want a model to be too simple, but you don't want it to be too complex, right? You want it to be a useful model. And so that's what you will be doing. You'll kind of be going through this process, kind of step by step in whatever your context is, right? How can we predict what the price of a home is? You look at lot size, you look at number of bedrooms, you look at number of bathrooms, you look at the year it was built, you look at whether it's brick or siding, right? You have all these different predictors. So you'll build a model with, the different variables that you think are the most appropriate. And then you'll let me know that you have a model that can predict house prices, right? And then you can say, okay, we could use this to build an investment firm, right? Real estate investment, big business, right? If there are houses that are undervalued relative to your model, then you can say, okay, we could buy this and then flip it and make a lot of money, right? So there's a reason why we might find use or utility in a model like this. So now we have a model that sort of meets our standards. We want to check if it's, a good model, right? And we have some diagnostics to help us check that. So the next thing that we want to do is we want to create diagnostic plots to evaluate normality, linearity, and homoskedasticity. So what are we going to do? We're going to grab our code from right here, and we'll paste it in. Now we're going to be plotting not from mod 3, but from Q2, right? Because Q2 is this model right here. It's the model from the Denver data set. that predicts X6 with X3, X4, X5 as predictors, right? So now we're going to get basically these 3 plots on this data set. So we look at our residuals. We see that there is kind of a slant in our residuals, which is something to notice, right? The QQ plot actually looks pretty good though, right? You do see a lot of the observations along the dotted line, though there's this one right here that is an outlier. It's also right here, right? This observation number 7. And so this might lead you to believe that observation, there's something weird going on there. And then of course, Hooke's distance is the best way to diagnose whether or not this kind of outlier matters. And here's your observation number 7. And clearly something is going on here where it is a highly influential observation, right? And so if we were to look at our data, right, where's Denver? Right up here. Let's look at observation number 7. So X6 is our crime rate, 704, right? So you look at all of the other crime rates, they're like 80, 170, 150, 60, 130, 170, 130, 108, 104, 60, 258 is not bad, right? It's kind of high, but nothing comes close to that 704, right? So that's a huge outlier. And so you might ask yourself, okay, in our data collection, we noticed that there was this huge spike in crime in neighborhood number 7. What happened, right? Is this something that we should be worried about in terms of its impact on our model? Let's say it's the kind of thing that doesn't actually, theoretically, it's distinct from crime in Denver neighborhoods. Let's say it's a bunch of Canadians, right? A bunch of Canadians went down to Denver and committed a crime spree, right? It doesn't really have any effect on that neighborhood. It doesn't have any effect on Denver. It was a one-off freak incident, right? And the Canadians have all been locked up or they're sent back to their country or whatever the situation may be. And so that 701 and that 704 in that neighborhood, right? It's an outlier that theoretically we can get rid of it, right? We can believe that the event that caused that outlier was such a one-off that it's not something we need to worry about, right? Now, if that's the case, then we can filter it out, right? We know how to filter. We can say we're going to filter everything where X6 is above 700. And that's an easy way, because this is a small data set, right? It's an easy way to just say, okay, we want to get rid of observation number 7. And then we can rerun it and see what happens, right? But the thing to note, right, is that we want to make sure that there is a theoretically justifiable reason for just getting rid of an outlier, right? If that outlier is theoretically meaningful, if that is actually a hotbed of crime in that neighborhood, right, for whatever reason, relative to Denver, specific to Denver, then that outlier is theoretically meaningful, and you can't really just get rid of it without some explanation, right? Without some theoretically justifiable reason to do it, right? So those are our first 3 diagnostic plots. The next thing that we wanted to do was multicollinearity, right? Because what did we use? We used 3, 4, and 5. So let's see what 3, 4, and 5 are. 3 are percentage of children. 4 is percentage of free lunch participation. And then percent change in household income, right? So there might be some overlap between some of these things, right? Like percent change in household income or percent free lunch participation. Maybe not, right? Because percent change in household income is a dynamic measure, right? It's change over time versus free lunch participation is a static number. So maybe not, right? We'll find out what those VIF numbers are. So VIF, so that's library car, companion to regression, and then VIF of Q2, right? Library car, VIF Q2. We can see that our variance inflation factors very low, right? X3 and X4 are about 1.25, but they're well below our cutoff, which we said was 10, right? Maybe 5 is where you start to get risky. 10 was our hard cutoff. Variance inflation factors well below the cutoff, which means we're not worried about multicollinearity creating instability in our model, right? So what are we worried about? We're worried about, the way that the residuals are plotted, right? The residuals are skewed below the even point. Why is that the case? Probably because this residual is so high, right? which means that the best fit line is skewed based on that one outlier, which means that the majority of the residuals are below the line, right? Which sort of makes sense. If you were to get rid of this, this outlier point, then you'd probably fix this residual plot, right? But the QQ plot looks good. Cook's distance is still, that's that one observation. It's doing a lot of work in the model. So if we can come up with a good reason to get rid of it, it will increase the overall quality of the model for us to do so, right? So what was the last thing that I asked us to do? Variance inflation factors. Do we pass all the diagnostic tests? No. What might the next steps be? Well, we should look carefully at that one outlier, and we should see if there's a way to get rid of it. And if we get rid of it, the majority of our problems are going to be solved, right? But we need a good reason to do so. We can't just throw data away willy-nilly, right? But if there's a good theoretically justifiable reason to get rid of that data point, then we can do it, and that's going to definitely increase the quality of our model. Any questions about what we did in this exercise? How much does that mirror the way that you went about doing stats in your stats class, right? You've done, I know that you've all done this before, right? With various kind of levels of retention. But how closely does this process mirror the one that you've seen? Let's do a 1 through 5, right? And just, you know, it's kind of a strange question, but I'm curious. How closely does what we just did mirror the way that you've looked at multiple linear regressions in your stats work in the last few years? You in class 1 through 5, was it pretty similar? Pretty similar, pretty similar? Okay. So 3s and 4s. So that's good. I hope that, so this is, like we said, you know, like I've said at the beginning of the semester, like I've said many times, this is an applied analytics class, right? So there's times where we're not going to get into the stats, where the stats are just too mathy or too complicated. We're not going to worry about that. But instead what we say is, okay, what are we looking for? We're looking for this number above this cutoff, or we're looking for this line to be straight or something like that, right? And then if you want to get into what these, you know, what these words mean and what these concepts are, that's for your stats class. So, you know, I anticipate that it'll be a little bit different from your stats class, but also hopefully we'll bring back some fond memories from last year or whenever that was. So we'll close up shop here. Next class, we will, so next class, I want to talk to each group individually to get a sense of where you are on your final project. So what we'll do is we will, I'll send out an email and we'll kind of set up maybe 5 to 10 minute individual sessions with your group. We can get a sense of, okay, what does the data look like? What's your kind of strategy going forward, et cetera. So I think this is what I have on the syllabus, and I'm gonna hold on to that day, that idea. So I'm not gonna come into class on Wednesday. I'm not gonna be here. But if you can with your group, be ready to say, okay, we looked at the data. This is kind of our general thought process. And this is where we are right now. And then I'll kind of make sure that we're all on the same page as we move forward with the project. So that's what we'll do next class. And then moving forward, we're going to do one more linear regression thing we're going to do with categorical variables, which you may remember, dummy coded variables, the reference group, all that. Hopefully it's not too far from what, or removed from what you remember. And then we're going to do logistic regressions after that. So that's what's next. So next class, I'm not going to be here. I'll take meetings within your groups, and we'll see if we can kind of get those group projects running. And then we're going to do a little bit more predictive work and regressions, and then do logistic. All right. So I will see you all on Wednesday.
Hey, Dr. Jip, I got one quick question. Once the class is over. Do you mind if I share my screen?
Yep. Let me give you permission to do so. Okay. I know I didn't respond to your email yet, but let's see what you've got going on here.
Yeah. Like I say, you're teaching the stupidest person in the program.
Well, so I did see that in your email, and first of all, I don't think that's true. But if it is, then I appreciate your sort of your willingness to work through it, right? I do appreciate that a lot because I know that it's not easy. All right. Okay.
But for the life of me, I don't know why fun, y equals. Only thing I can think about is I need to have another line that says monthly sales, or sales is monthly sales.
Okay, so sales. Okay, so I think that you need to close your parentheses on line 26. Group equals month. Yep, you need to close that parentheses.
Okay.
And then you've got stat summary, so you need to get rid of one parentheses there.
Yep.
And then you've got color equals month. That's good. Does it look like you've got one extra parenthesis? So you need another parenthesis on the top and then one fewer on that next line. So
Okay.
one more in 26 and one fewer in 27.
Okay. So
get
right
rid of add a parenthesis there.
Yep.
And then get rid of one on 27. All right. Now try running that. Okay. So the stats summary failed. Find y equals sum geom line aesthetic color equals month. Okay, so let's let me pull up my okay. What was that error message? Removed containing non-finite values. Okay, so okay. So here's the thing, right? Your issue is on line 21. Because if you look at the environment, your coffee has 0 observations of 22 variables. So that means that there's a problem with a filter. And what is the problem with the filter? It might be that try getting rid of the quotes around 1, 2, 11, and 12.
Okay.
Have you turned that into factory? Well, we'll try that. We'll see what happens.
Why is it so slow?
Now we're on line 21. Okay, what's the message? Filter. Okay, let's see. Well, that's where the issue is, right? And we know that because if you look in the environment, it has 0 observations there. So let's see if we can figure out how we could do a filter. Let's find some example code that we can look at. Let's open Okay, so. Okay, filter. Can you click the little table thing for next to coffee chain 2, just, and scroll to the right to make sure that we have year, month, and day as new columns, just so we can double check. Ah, okay. Looks like that's the problem now.
Okay.
Okay, so we got to keep working back. It looked like that worked okay, but let's see what the issue was. All right, so pop back over to the script. Okay, so date is MDY date, and then coffee chain to year. Okay, so run line 15. Okay, then run line 16. All right, then pop back over to coffee chain. Let's see if that did anything. It did not. All right, so let's see what happened here.
MDY.
MDY coffee chain 2 $sign date.
I looked through all these right here, and I just obviously I went.
Yeah, I mean MDY should work. Okay, so let's see. Somewhere type in like head coffee chain 2. We want to see the header. We want to see what data type that is. If we want to see if MDY worked.
You said head.
Yeah, head coffee chain 2. The full data set.
Run it.
Yep. Okay, so we've got date is in date format. So that's good. That's good news. So line 15 worked. So then we got to say line 16. Coffee chain 2 year is year coffee chain 2 date. Okay. Okay, this is going to be kind of a Hail Mary. So I don't know if it'll work, but we'll see. So on line 16,
Okay.
select kind of coffee chain 2 up until the end of that underscore. And then type the backtick. So hopefully that creates backticks around it.
Backtick. Okay.
Now run line 16. And check if that did anything in coffee chain 2. No, it did not. That's so weird.
Well, it makes you feel a little bit better in that we don't know.
Yeah. So on line 15, change the output to like date 2. So coffee chain 2, date 2 is going to be MDY coffee chain 2 date, just so we create a new column.
Okay. So put date 2.
Yeah, so just put a 2 there.
Yep.
and then run that line and then see what happens inside of Coffee Chain 2.
Is that another comment?
Okay, so that is okay. That's great. Try running the library lubridate, line 14, just in case. Now we're on line 15. All right, and then check Coffee Chain 2. Yeah, still nothing. It did make the column though. That's strange.
Should I take off the backticks and try it again?
Yeah, sure. I mean, I don't think that's going to do anything. The backticks, I think, will not make a difference, but
No.
okay, scroll up. Let's see what's at the top of that script.
All right, just my number 2. Oh, my number 1.
Okay.
I know I got. No.
Yeah. I don't know. I'm gonna have to take a look at this on my own machine. Is this the sort of the state where you sent me the email yesterday?
No. I'll resend it to you.
Okay, resend it to me, and I'm gonna close this call and then hop back in just so because my second class is logging in.
Okay.
And I just want to split the recording, so there's a recording for the first class and a recording for the second class. So I'm gonna log off, but yeah, shoot me this again. And this is gonna be my first priority as soon as I get home because I'm extremely confused about what the situation is. So
I
we'll figure it out.
I appreciate it.
All right, the code looks good, so you clearly understand it, but we'll have to figure out what the issue is. I'm not 100% sure.
Okay. Thank you for your time.
All right. Yep. Have a good afternoon.
All right.